Hello, today I'm going to talk about physically terraforming a hot planet, with Venus being the obvious candidate in our own solar system. Venus's surface has a temperature of nearly 500 degrees Celsius, that's 932 Fahrenheit, and a surface pressure 93 times that of Earth's. Venus's extreme temperatures are due to its thick carbon dioxide greenhouse atmosphere, which prevents infrared radiation from escaping into space. Venus would be an enormous challenge for terraformers due to its extreme temperatures and its massive atmosphere. With 92 times more atmosphere than Earth, it has far too much carbon dioxide, which is 96.5 of Venus's atmosphere, and even too much nitrogen, which is 3.5% of the atmosphere. Cooling its atmosphere, could be done with giant space sunshades, thousands of reflecting satellites, or clouds of dust which would block much of the sunlight reaching the planet. Alternatively, adding particles, balloons, chaff, or thin films of highly reflective material into the upper atmosphere might also help to cool the planet. If Venus's atmosphere was cooled, the loss of its thick cloud cover would decrease the albedo, the reflectiveness of the planet. The halving of the reflectiveness would double the amount of solar energy that it receives. This would work against the cooling efforts of the terraformers and would necessitate additional work to achieve further cooling. Many of the plans for reducing Venus's temperatures operate on lengthy time scales of thousands or even millions of years. However, some writers view Venus's atmosphere as a valuable resource. If we take this approach, rather than seeing it as an issue that requires a solution, humans will have an excellent source of carbon, oxygen, and nitrogen for thousands of years to come. If they eventually deplete this resource, perhaps then they can consider terraforming Venus. Venus's atmosphere is primarily composed of carbon dioxide, but with some nitrogen as well. Thus, it may be possible that they might be useful resources for terraforming Mars, for example. However, Venus's atmosphere has 3 times more nitrogen than Earth's, and many times more carbon, oxygen, and nitrogen than would be required for terraforming Mars. Venus could be cooled by injecting its atmosphere into space, either during massive asteroid impacts or by exploding nuclear devices. However, these gases would then pollute the inner solar system. On Earth, we already have over 400 parts per million of carbon dioxide, which is increasing our temperatures. Increasing this amount could sterilize our planet, so polluting the inner solar system is really a no-no. Several writers have suggested that Venus's atmosphere could be solidified, for example, by rearranging carbon dioxide into a 3-dimensional tetrahedral form, by sourcing hydrogen from the gas giant planets and reacting this with carbon dioxide to produce elemental carbon and water, or by using pure iron to scavenge oxygen from carbon dioxide, leaving elemental carbon, or using calcium and magnesium from Mercury, the planet Mercury, to turn Venus's atmosphere into carbonates. However, it may be easier to extract gas from the top of Venus's atmosphere than hoisting solids through the planet's atmosphere and gravity well. Various writers have suggested placing scoop ships into elliptical orbits around Venus, dipping into the atmosphere at their closest approach to collect gas, for example. Some have suggested that tube skyhooks, space elevators, or rotating tethers could be deployed to collect supplies of carbon dioxide for use elsewhere in the solar system. However, the wind speeds at over 100 meters per second, faster than a hurricane on Earth, have been seen above Venus's cloud tops, which could be a major problem for atmosphere miners. Other ideas include shipping gaseous carbon dioxide around the solar system in tanker spacecraft, but this would require huge numbers and vast volumes. If it were possible to accelerate the gas to a high velocity, it might be possible to direct it at specific targets, almost like a laser, such as Mars, and to keep the carbon dioxide stream thin and tight by using methods such as ionization or charging some of the gas. It would seem better to avoid Earth's orbit altogether by directing the gas either above or below the plane of the solar system. Ideas around terraforming Venus and the accessing of its atmospheric resources fall into the middle ground between science and science fiction. Venus's atmosphere may be the inner solar system's largest supplies depot, containing massive amounts of oxygen, carbon, and nitrogen, which would supply an interplanetary civilization for thousands of years. There's no harm in discussing these topics many hundreds of years before they would be put into action, as theories and concepts which are developed today might be the foundation of the engineering realities of tomorrow. Only once the majority of Venus's atmosphere has been extracted would the possibility of terraforming the planet become a reality. As we don't know what technologies our descendants will have in 1,000 years' time, we can't predict when or if they will be able to do this. If the majority of Venus's atmosphere was extracted, the removal of a great weight pressing down on the crust would result in isostatic readjustment, which we see on Earth after the melting of glaciers. This means that the land would rise in some areas, resulting in earthquakes and a period of intense volcanism, making life on the surface very dangerous for any colonists. So that has to be taken into account if the atmosphere were removed before proper biological terraforming would take place. Venus's retrograde spin, rotating once every 243 days, is tidally locked with Earth, so that Venus takes the same time to orbit the Sun 13 times as Earth does to orbit 5 times. During the same 5-year period, Venus spins 12 times. This means that each day on Venus is equivalent to 117 Earth days, which could be a problem for living organisms on a terraformed Venus, as nights would be very long, cold and dark without a moon, and the days exactly the opposite, far too hot. Thus, for life to exist on a slow rotation planet like Venus, more frequent light and dark periods would need to be in place. Otherwise, the long periods of cold, dark, and hot and bright would kill almost anything on the surface within a few years. It may be possible to install a system of orbiting mirrors or lenses to reflect or refract the sun's light on a 24-hour basis. Schemes such as these have been proposed as ways to generate power by focusing the sun's energy onto single collection points on Earth. However, numerous mirrors or lenses of considerable size would be required to light the whole of Venus's dark side. Unless they were huge, they would not be enough to prevent the cumulative nighttime temperature drops. Increasing Venus's spin by transferring angular momentum from Jupiter using an asteroid is another option. The asteroid would need to orbit both planets without being intercepted by the Sun, Mercury, or Earth, and would need to take tight turns around Venus and Jupiter without being broken apart by either planet's gravity. The same sort of angular momentum transfer could use the Sun as a source of the momentum. This might be more achievable than with the relative proximity and only one planet, Mercury, between the Sun and Venus, as the path of the asteroid is likely to be more straightforward. However, it could take thousands or even millions of years to change Venus's day from 117 days to 24 Earth hours. Another problem is that Venus has a retrograde clockwise spin, whereas the Sun rotates in the opposite anti-clockwise direction. This means that the transfer asteroid transferring angular momentum would need to travel a complex figure of 8 path between Venus and the Sun. Another approach would be to increase Venus's spin using asteroid impacts. However, there may not be enough asteroids in the solar system to do this, and the most useful ones, the metal-rich ones, may be needed for mining and for our technology. A very different approach would be to achieve a 24-hour day using what they call a para-terraformed roof, or an atmosphere-retaining envelope called a world house, which would be erected over the whole of the planet's surface. This would be like a balloon right round the outside of the planet. The underside of this artificial sky could be used as a screen to project images of the sun, moon, and stars to simulate daylight and nighttime on an enormous, high-energy, flat-screen television. The outer surface of this roof layer would capture the energy needed to take this mega TV into working function. Trying to guess which technologies our descendants will have in 1,000 years' time is like people in the year 1,000 years ago trying to forecast computers, air travel, and nuclear power. This means that the things our descendants will be able to achieve will be well beyond our expectations today. Today, we can only base our best guesses on the laws of physics and our own capability for imagination. Anyway, thanks for watching.